Hello. I already started a recording and my brain stopped working, so I stopped it. So we are just starting with all of this written on the board. Okay. So this is number 5, and then we are doing number 6 because number 5 is this initial setup, but number 6 is going to be this function broken into 2 pieces, but rather than rotating around an axis, we are going to be rotating around our line y equals 2. So for this, helps to visualize what's happening. So what's happening is I'm actually going to take this section here and flip it up and over and around this y-axis. So what I actually need to do here, since we're not just rotating right up against a line that we normally would do, I actually need to set this up as 2 radiuses for this problem. So I'm always going to do my outer radius minus my inner radius. So with these problems, when we're setting these up, I think it helps to set up which one's your outer radius and which one's your inner radius, because it's always going to be outer minus inner, and that helps us set up our problem correctly. So if we think about it, if this whole thing is going to get flipped up and around, the part that is technically our outer radius is going to be our axis, our x-axis. If I go back to our problem, I believe it says that very specifically. Yes, it says the first quadrant. So the first quadrant is telling us that it stops at this point, basically, or at this line. So when this gets flipped up and around, this length 2 minus 0 is how we get that. That is going to be our outer radius. Or just 2. There she is. Outer radius is going to be 2. So now we need to find our inner radius. Our inner radius is going to be different depending on which section it is in. So this is going to kind of be like a loaded problem. So our inner radius for this one is not going to be too bad. So from the interval 0 to 1, our inner radius is just going to be, sticking with this form, it's going to be 2 minus whatever our function is. So in this case, it is going to be 2 minus 1. So I'm going to say my inner radius is going to be 2 minus 1, or just 1. There she is. And then my inner radius for this guy is going to be 2 minus this function. So it's going to be 2 minus x, or positive x, since we're going to distribute our negative. So this is just going to be x. So when we set this up, this is our base function. I need to set this up on 2 different boundaries because I have 2 different inner radiuses. So I'm going to set up my first one from 0 to 1, and it is still going to be times pi. And what I can do, since I'm going to have some subtraction going on here, it's really helpful just to bring the pi on the outside of the integral so we don't have to worry about it, we don't have to distribute it, and kind of just save it for the end. And then we're always going to do our outer radius minus our inner radius, and these individual things are going to be squared. So we're going to do 2 squared minus 1 squared, and that is going to be with respect of x, because we are rotating about the y-axis. This is the only time I wish we were here, because I'm not sure how you feel about these, because this just took me a little bit to understand conceptually. But basically, I think about whichever way that you are spinning. So since we're spinning vertically here, we need to make sure that whatever is on the outside of our interval, like whatever variable we are utilizing, is going to be the one that we are splitting up into tiny little pieces. So here I'm spinning around this axis a whole bunch of times as thinly as I possibly can. So that's what's happening. So that's why I'm doing this with respect to x. And whenever we spin around the y-axis, that's when we have to do it with respect to y. So that's what that is. So we set up this subtraction to get rid of this empty area basically, but I need to now add a second area because I just did from 0 to 1, so now I need to do from 1 to 2. And this is going to be still set up outer radius minus, now my inner radius is x, and we're still going to square this because that just is our base formula. So that's how we would set it up. I'm going to try to fly through the actual computation of this just because this isn't a difficult computation problem. So this is from 0 to 1, 1 to 2, 4 minus x squared, and then this would be pi times 3x, and then this is going to be 4x minus 1/3 x cubed, 1 to 2, and we're going to have to distribute our pi all the way at the very end. There she is. And after computating that out, I get 14 over pi, and I believe that that is what she got as well. I've been referring to the answers. I did notice that there are some answers that are incorrect. So that could be why you sent me some of the problems that you did. So I will address that for each problem where I found an error. Not a lot, but definitely more so towards the end, which is aggravating, but it is what it is. People make mistakes. Yes, she got 14 over pi. So if you were to evaluate that, and just because I trust you, so I'm not going to do all that because it's a Sunday and we have a lot of problems to get through. So, but the actual setup's the tough part for this guy. So that is how we set this up. It's understanding definitely outer minus inner. It's understanding that when we have a line that is not the axis, we are doing, when it is above, we are doing your line minus whatever your functions are, if it's greater than, basically. And if you're not sure, because it's kind of harder for this to make sense, always just throw a number in there, because I think it makes sense to have this radius as 1. So if you're like, well, I know that that distance is 1, then do whatever you did to get 1 to minus 1 in this instance, and do the same thing to the other function that maybe isn't as conceptually easy to write. So that's what I would say for this problem. And let me know if you have any questions, and we can always talk about it more. So we will move on to the next one. My goodness. Okay, so what one are we doing? Next, number 10. Evaluate this integration by parts. Just triple checking. Yep, you said number 10. So this is going to be all right, and we're just going to need a plus c at the end of this. So this comes from just knowing our integration by parts formula. So if we have the integral of u dv, make sure you can see this. If we have our integral of u dv, so this is going to be something times something. So whenever we're kind of looking at things and like what technique to use, whenever you have something times something, integration by parts is normally a good way to go. And then this equals uv minus the integral of v du, I believe. I believe so. So normally we set this up as u equals something and then dv equals something. So again, just thinking about how to know which problem or which to set up, we have to take the derivative of whatever we set u equal to, and we have to take the integral of whatever we set dv equal to. So normally, if you have a linear equation, whenever we take the integral of this, that basically takes our funkiness away. We don't care if we have any coefficients floating around, because coefficients just end up floating around when we integrate or differentiate. So this is actually going to, if we set it as our u, when we derive this, it's just going to go to 5, which makes it an easier integral for us down the line when we actually utilize this formula. So I'm going to set my u to 5x and my dv to cosine 2x. There. So I need my du, and that is just going to be my derivative of u, and my derivative of 5x is just 5. And then my integral of cosine 2x, we would actually need to do u substitution in this instance. We'll just go through it, and I won't go through it in later problems because it is pretty consistent with all of the trigonometric ones. We won't do u substitute. We'll call it like w substitution to kind of keep our variables floating around. So if I have, let's say, cosine 2x dx, if I set my w equal to 2x, then I need my dw dx, I need to take my derivative of this. That would equal 2. I have a dx here. I have a dx here. So I can solve for that dx with just some algebra. I can multiply by dx on both sides. And then I have dw 2 dx. And then I can divide by 2 here. So that is going to get my dx equal to dw over 2. So here I have cosine of w, because we set that equal to 2x, and then we have dw over 2, and then I just take the integral of this, so this would equal, since I have divided by 2, I can just write that as 1/2, and then my integral of cosine, derivative of sine, is cosine, so my integral of cosine is sine of w, or 1/2 sine of 2x plus c is what that ends up being. So basically, whenever you are integrating, and apologies if you're well versed in this, I'm just not sure, but whenever we take the integral of anything that has a linear function in our parentheses there that I didn't write, but cosine of this, sine of this, so on and so forth. We're just going to divide by whatever the derivative is of the inside. So it comes with time, but definitely I won't be going through that every single problem that we go through here. But that is what that ends up being. Yes. Okay. So I'll erase all of my u substitution work. All right, so now I'm just going to apply this formula. So I have a u and a v. There she is. So I'm just going to say this is 5x times 1/2, or just 5x divided by 2, times sine 2x minus the integral of v 1/2 sine 2x times 5 dx. That's where that dx comes from. there she is. That's correct. So now I can say 5 halves x sine 2x minus 5 halves integral of sine 2x dx. So here I can do another u substitution that I'm not going to walk through the steps of, because all I'm going to do is just divide by whatever the integral is in my sine. So the integral of sine, derivative of sine is cosine, derivative of cosine is negative sine. So this is going to be negative cosine times 1/2. And if we were to do the u substitution, we would end up getting that. So this is just going to be plus 5/4 cosine 2x plus c. That's what I got in my notes. Let me see if this is what she got. That's nice. Yep, 5 halves x sine 2x plus 5/4 cosine 2x plus c. And she seems really specific with how she wants these things notated. I'm not sure how she's been on prior grading, but if you were just thinking about how you would write all this on the exam, I would go off of her notes, because she definitely uses proper notation the entire time, which is nice, but I don't know if she's going to dock points. Like when she put this step in there, she said integration by parts, and stuff like that. So I would just be mindful. Definitely with series, she seems like she would expect all of the words written like by the comparison test, especially because she has that whole sheet saying what work is expected for each part of the problem. So I think that is something that I would focus on as you're studying, but that's just my recommendation. I don't know how she's graded your prior exam, so she may not be as strict as she is saying that she's going to be. So who knows? All right, moving right along to number 14. In my head, I wanted to write these numbers just in case you're skipping through these problems, so I will start doing that as of now. This is number 14. I go to this. Oh, trig substitution. This one actually didn't end up being as bad as I thought it was going to be, because I feel like trig substitution can take a whole notebook page very easily, but I didn't think that this one was as bad as it could have been. Let me just say that. All right, so there are 3 different trig substitution guys. So it's knowing whether you have the square root of a squared minus x squared, the square root of x squared minus a squared, or the square root of x squared plus a squared. And obviously that last one could be written either way, because it's plus, so it doesn't matter what order they're in, but for these, they do matter. The one that we have is going to be, a is just going to be whatever constant we have. So here we have 16, which could be written as 4 squared. So here we actually have a squared minus x squared. So this is the one that we are going to be using. And with this one, I'm going to erase our other ones. This one is associated with our sine function. So we are going to have x equals a sine theta. So here, since we have 16 and we want a squared, a is just going to be the square root of whatever this number is. So this, our x, is actually going to be 4 sine theta. That's what our x is going to be. And we are going to need dx as well. So with all of this stuff, notation really comes, obviously, very heavy into play. I don't know. So we just need to be mindful of that, basically. So we have dx d theta equals, derivative of sine is cosine, so this would be 4 cosine theta, and then if we just want dx, we would multiply by d theta on both sides, and that's how we get that. So now we can actually substitute these things in because I have an x here, and a dx here, and I have a whole bunch of things to plug into this. So I can say we have 4 sine theta over square root of 16 minus x squared, which is 4 sine theta squared. Dx is 4 cosine theta d theta. And with all of these problems, and definitely with the shell method and disk and washer and all that stuff, and this type of stuff too, notation, having every single variable in your integral being the same is a great check to make sure that you didn't miss anything. Some of these you can kind of set up a couple different ways, and they're all going to be accurate as long as you're just consistent with all of your variables. That will come into play later. All right, so if we square this, so this is going to be square root of 16 minus 16 sine squared theta. And then we have a 16 and a 16, so we can actually, I'm going to do this over here. I don't think I'll run out of space, but I'm going to do this over here. So we'll see. So if I have 16 minus 16 sine squared, I can pull out a 16 and say that is 16 times 1 minus 1 sine squared theta. And there is actually a trig identity for this. So 1 minus sine squared theta is equivalent to cosine squared theta because cosine squared theta plus sine squared theta equals 1. So if you just subtract one of those from either side, that's how we remember that that's a trig identity. This is one I often forget. So this is actually going to be 16 cosine squared theta. That's what this ends up being. And we could take this and put her back under there, which is nice because now I don't have a addition or subtraction sign. Whenever you have an addition or subtraction sign within your square roots, it's a pain, so it's nice to get rid of them. So I can actually take the square root of these two things because they're just multiplied by each other. So I'll write that step out just so everything's written. This would end up being 4 cosine theta. And this is 4 cosine theta. So that, we're running out of space, but these end up canceling. And all we have is 4 sine theta d theta at the end of this. And we know that integral of sine is negative cosine. So this is going to be negative 4 cosine theta plus c, because this is not a definite integral. And then all we need to do is find what theta equals. I'll do this in this corner. So we need to use our Pythagorean theorem here. So we have a triangle. All right. I normally just do my angle in the lower right corner because that's just how my brain works. We have this that we have set up. So I understand, I guess more accurately this one, because that actually gives me some information. That is what we're going to use to be able to figure out what cosine of theta is. So I need sine theta. Sine of theta, if I solve for this, is going to be x over 4 equals sine theta, because I can divide by 4 and find out what sine of theta is. Sine, if we remember trigonometry, is going to be opposite over adjacent. So from this angle, opposite is going to be x, and not adjacent, hypotenuse, opposite over hypotenuse. There she is. And this we'll just call A. We're not sure what she is. Well, I already have an A up here, so I'll call her B. So I'll say B. But I can find B by using a Pythagorean theorem, because I know b squared plus x squared equals 4 squared through my Pythagorean theorem. So I have b squared plus x squared equals 4 squared. I want to find B because I need cosine of theta. So I'm going to need to know what B is so that I can plug cosine of theta back into this equation. So if I solve for B, I can subtract x squared from both sides and take the square root. So that will end up being 16 minus x squared, and the square root of that equals B. And then cosine of theta is going to be adjacent over hypotenuse. So cosine of theta is going to be square root of 16 minus x squared divided by 4. Let's see. I lost my space. And then all we have is just our 4's end up canceling. And this just ends up being negative square root of 16 minus x squared plus c. Very tiny at the end. But that is where that ends up coming from. Of all trig problems, or trig substitution problems, I think that this is a pretty tame one, which is crazy to hear, but it really could be worse. So it's nice to take the little wins. And yes, that is what she got. So we are all aligned there. No issues there. All right. How am I doing on time? I'm at 28 minutes. That's 3 problems. So I'm going to pause, upload, and then we'll keep going, and I'll label these part 1, part 2, part 3, etc. All right.